let's take a look at this final task here, Sudoku. All right, so in case you're not familiar, Sudoku is a number placement puzzle. Okay, so it's basically, normally we start out and we don't have like all these numbers in here. We got to fill them in ourselves based on deductive reasoning. And the idea is that every row, every column, and every one of these 9 squares that you can sort of see it's divided in with the darker lines here, every one of those needs to contain the numbers 1 to 9, and like exactly those numbers and only those numbers. That's the idea. So in this task, we're basically given a completed Sudoku, completed puzzle, and we want to tell, is this valid? Like, is it okay? Did they do something illegal here? So like, for example, in this case, we're saying this one's invalid for 6 reasons. And all of them are basically the same thing. We have a duplicate number appearing in the same square. We have that a bunch of times here. Now, keep in mind, there are lots of other ways that this could fail. Like, for example, if one of the rows had like 2 1s in it or something like that, or if a column had 3 7s or something. Like you can't have more than one of the same number in a row, a column, or a square. A 3 by 3 square. I mean, yeah. Subgrids. Anyway, the point is, that's what we want to do. So we want to verify this thing. We're given this completed one, and we want to say, is that valid? Is that legitimate? So that's basically the idea. Now, in terms of how we're actually going to go through and do this, well, I guess there are a few ways. I mean, like, we could go through every row and just check, like, do you have numbers 1 to 9? Do you have numbers 1 to 9? Numbers 1 to 9? Numbers 1 to 9? And then we could do the same thing for each of the columns, and then we could do the same thing for like each of the squares. So, it's tempting to want to start with that, but I feel inclined not to. And the reason is because, we would basically be looping through the entire matrix 3 times if we did it that way. And that just feels a little too inefficient, I think. Instead, what we can do is just go through the matrix 1 time. Just look at this element, this element, this element, that one, etc. Just go through every row. Well, I mean, that's the thing. We're going through every element, and we can basically just say, let's say it's this element, this 1 over here. Well, basically, the idea is that the 1, and in fact, here, since we have the tools, we might as well do this. Okay, so we've got the 1 here, and basically the idea is that it belongs to the row with index 3, it belongs to the column with index 2, and it belongs to this square, which I'm not sure what index this would have, maybe 3, like 0, 1, 2, 3, 4, 5, 6, 7, 8, something like that. So that's the idea. This one, we don't need to go through it 3 times to be able to tell which row, column, and square this belongs to. That's just determined by the indices here. That's the idea. So here's what we're going to do. Let's create some arrays to begin with. So we'll say let rows be this empty array, let columns be this empty array, and let squares be that empty array. That's basically the word squares, except I took out all the vowels. The main thing is I just wanted to have it line up nicely, so 4 characters for each. But, if that's unclear, we could use the entire word squares. That would work too. It just wouldn't be as nicely aligned. Anyway, the point is, so we've got these 3 things, and then basically what I want to do is go through the entire matrix here. So I'm going to do a nested loop. Now, normally I would do something like I is less than grid.length or something like that, but we know that this is going to be a 9 by 9 square. That's a guarantee. And actually, we might as well take a look at this now. So basically, yeah, it's going to be a 9 by 9 grid. And it's filled with numbers specifically from 1 to 9. And that's maybe going to be an important fact, the fact that we're not going to have like 27 in here or something like that. Okay, so basically, we know it's going to be 9 by 9, so we don't need to worry about like other indices or anything like that. We know it's just going to be the numbers 1 to 9, and so maybe that could help us out a little bit. Yeah, maybe. So anyway, here's what we want to do. We basically have this array of rows, we've got an array of columns, we've got an array of squares. What do we want to do with each of these things though? So I guess basically what we want is, okay, there are a few ways we could do this. You know, we could say like for let I be assigned the value 0, I is less than 9, I plus plus. And then for each of these, we could say like put a new array into each of these things, right? So we could say like rows dot push, and then just do like a new array that's like array with a length of 9 dot fill 0, you know, something like that. So basically we have an array of length 9, and it starts out as all just being zeros. And then we can do the same thing for columns and squares. And then basically the idea is we're going to have something pretty large here, I guess. So, all right, let's take a look at what this is looking like. So let's just return rows for now. Okay, yeah, big. I mean, it looks like the same grid here, but all zeros pretty much. So is that going to be useful for us? Yeah, I guess so. I mean, we could do something like this, right? We go through and basically say, okay, first of all, let number be assigned the value of grid at I at j. Okay, so that's going to be the number we're looking at, you know, at these particular indices, whatever 1 to 9 we have in that spot, basically. Okay, so that's going to be our number. And what we want to do is basically this. We'll say rows at I, okay, so that's the ith row, right? That's, you know, like let's say the index I was like 2, we would be looking at this row in that case, so the row with index 2. And then specifically within that, we want to say the index, like the thing in that array, sorry, this one, the thing in that one at the index that's basically this number. Like I wanted 9 of these things because one of them for each number. That's sort of the idea. Okay, so rows at I, at number, and I'm going to put a -1 because keep in mind the numbers go from 1 to 9. The indices here go from 0 to 8. So I'm putting in the -1 there. And basically, I just want to do a plus on that. I mean, yeah, that's basically it. And I also want to do like columns at I, at number -1 plus. But actually, technically I is not the column number. It would actually be j that would be the column number. And then we'll do the same thing with squares. Squares at k, let's say, which we'll define in just a second. And number -1 plus. There we go. Okay, so what's this k value? Well, we want something that's basically going to give us, like we were saying before, like, let me get a sick color in here. Okay, cool. So we want something that's basically going to say that's 0 square, that's 1, that's 2, this one's going to be 3, that's 4, that's 5, 6, 7, and finally 8. Okay, so how are we going to do this? Well, first of all, notice that like for the indices in here, for I and j values anywhere between 0 and 3, well, 0, 1, or 2 basically, we're going to get a 0 for this. So probably we'll do something like a Math.floor of I divided by 3, j divided by 3, something like that. Because if we do that, let's just say we're talking about j, you know, so we're going left to right. If we do a Math.floor of j divided by 3, then basically 0, we divide it by 3, round down, we get 0. 1 divided by 3, round down, we get 0. 2 divided by 3, round down, we get 0. 3 divided by 3, round down, we get 1. Same with 4 and 5. We move on to 6, 7, and 8. Those will give us 2. Okay, cool. But then the thing is, once j is back to 0 over here, we would just get a 0 again. So basically, we sort of want to add in the I there. For the i's, notice we're not just going 0, 1, 2. We're going 0, 3, 6. So we'll do the same thing. We'll do like a Math.floor of I divided by 3. We'll actually multiply that one by 3 because we've got 0, 3, 6. And then basically those same numbers, but plus 1. So 1, 4, 7. And then plus 2, 2, 5, 8. So basically, our formula is going to be something like this. It's going to be the floor of I divided by 3 plus the floor of j divided by 3. Whoa, that was a weird 3. And this one is going to get multiplied by 3. So we're going to have 3 times the floor divided by 3 plus the floor of j divided by 3. That's the idea. Okay, so let's do that. We'll say let k be assigned the value of 3 times Math.floor of, what was it, I divided by 3? Yeah, plus j divided by 3. I mean, I suppose it doesn't really matter which order we put these in, and I don't want to forget my Math.floor there. Very important. Okay, cool. Nice stuff. So let's run that, and yeah, it's not doing anything. It's not returning anything, so maybe we should return something. Let's return, I don't know, rows for now. Let's just see what we're getting. And okay, so notice it's basically a whole bunch of 1s, but then like a couple 0s and a couple 2s. Well, what does that mean? It basically means we found almost every number exactly once in every row. Except there were some rows, like the 0th and the first row, they actually doubled up on some numbers. So in this one, instead of having an 8, we had 2 2s. Let's verify that. So if we look at this first row here, or 0th row, yeah, we don't have an 8, but we do have 2 2s. Well, that's no good. We shouldn't have that, right? So basically what we'll do here is something like this. If we basically want to say, well, if that number is already there, that's not good, you know? Like if there's already a 1 in the spot here, instead of just incrementing it again, like doing another plus plus, I basically want to say, well, don't go any further, because you can't. Like return false at that point. That's it's not going to work. So basically we'll say if rows at I at number -1, or calls at j at number -1, or squares at k at number -1. If any of those are already something that's not 0, so in other words, if any of these are something that would be typecast to true, then we basically just want to return a big old false, because we're saying, hey, you already found that number. It's a duplicate. This isn't going to work. It's not a legitimate Sudoku. Okay, so is that going to work? Let's find out. Ooh, all right, it's passing the visible ones. Let's see if it's going to crush the hidden tests as well. Oh, and it does. And look at that. That brings us up to 100%. Okay, you guys ready for this? This is a big moment right now. Oh, look at that. 50,000 coins? That's like half of what I already had. So, okay, important lesson here. So check it out. Let's just close that for now. If you complete the arcade intro section, depending on how long it takes you, because you get 500 coins every time you sign in per day, depending on how long it takes you, you should be looking at about 150,000 coins. That's not bad. That's not bad. Okay, so look forward to that. As for now, I want to think about some other ways that we can handle this thing. So, what are some other ways that we could handle this thing? All right, well, I mean, like, we could use an object or something like that. I mean, technically, like, we're talking about a situation where we're just looking at, like, a 1 or a 0, pretty much, right? So, maybe there's a different way we could handle it. So, I guess what I'm trying to say is, this plus plus business, it's basically just flipping it from being false to being true. I could have just as easily made all of these false values and then made this like, is assigned the value of true instead of a plus plus. Okay, but what I want to do now is more, well, it's going to be something a little bit different. Yeah. So the first thing I want to do is, what's the first thing I want to do, actually? Well, basically, what we could say right off the bat is, I'm looking at this double for loop here, and, it's pretty good. It's not bad, but we could probably pull it off with an alternative strategy. So here, we'll do one of these. We'll copy all this stuff, And we're going to continue with it up here. And we'll call this one Sudoku 1. Okay, cool. So now, okay. I want to make a few changes here. I'm just trying to think of like what order we should make the changes in. So here, let's make this first of all just like I guess a single loop. Should we do it that way? Is that a good idea? I'm not sure. Maybe we'll keep it 2 loops for now. But okay, so we've got this idea here where we've got this number. I kind of want to try this a bit differently though. So basically what we can do is, okay. First, let's do it this way. So instead of doing like all this stuff here, you know, instead of having like arrays within arrays and stuff like that, I want to switch this up a little bit. So basically the idea now is that we're going to have, an array for rows, an array for columns, and an array for squares. Except what we want to do here that's going to be a little bit different is now, okay, we're not going to do this. We're not going to make these matrices anymore. We're just going to make them arrays. They're just going to go from 0 to 9. So each row is now going to be represented not by an entire array of values representing whether or not they have the number. They're going to be represented by just one number. And it's basically going to be, well, okay, here's the idea. We basically want to check if each of these rows, if each of these columns, and if each of these squares contains the numbers from 1 to 9 inclusively. So one way we could handle that is basically multiply all the numbers together. If we multiply all them together, we should get basically 9 factorial. That's the idea, right? Because it would be like 1 times 2 times 3 times 4, all the way up to 9. So we should get 9 factorial. And that should be the only way we can get that number. Pardon me. Because the idea is that these can only go from 1 to 9. There are going to be exactly 9 of them. The only way we could avoid that is if we had something that was like, for example, let's say maybe it was like, if it was missing one number, like if instead of a 6 it had 2 3s, but then instead of a 9 it had an 18, you know? So like basically something like that would multiply the same product. It would ultimately have the same factors, but we can't have an 18 because the numbers just go from 1 to 9. So the only way with these restrictions we're going to be able to get that 9 factorial by multiplying all these numbers together is if there's exactly one of each of these numbers from 1 to 9. So that's basically the idea. So what's 9 factorial anyway? Well, here, let's make a function for that. So it's going to be a function. It's going to be called factorial, and it's going to take in a number. How's this going to work? Well, basically, it's going to say if num, so basically if the number is something greater than 0, then we're going to return num, whatever that number is, times factorial at none minus 1. Otherwise, return 1. Yeah, that's the idea. So this is factorial. This is the way it's working. This is a good example of recursion. So basically the idea here is if the number is something greater than 0, we're going to say, so for example, if it's, let's say, 4. Okay, so we start with 4. It's going to say we've got 4 times factorial at 4 minus 1, which is 3. So 4 times factorial 3. Well, what's factorial of 3? Well, first of all, is 3? Yeah, it is. It's considered true. So basically, we'd say, all right, so that's going to be 3 times factorial at 2. What's factorial at 2? Well, 2 is true, so it's going to be 2 times factorial at 1. 1 is true, it's going to be 1 times factorial at 0. Factorial at 0, we'll say no, this is false, so it's just going to return 1. So if we return all those, basically we had 4 times 3 times 2 times 1 times 1, which should be 4 factorial. So I guess we can verify that. Factorial at 4, so it should be 24, I think. And yeah, it's 24. If we do 5, we should get, I think, 120. So let's make sure that's giving us the right number. And then if we can verify that, we'll jump to 9. Yeah, 120. So we'll jump to 9 now. What is 9 factorial? Oh, it's this number. Okay, so I'm just going to copy that. We'll hold on to that for the time being, I guess. In fact, let's just make a new function, and we'll just call it 9 factorial. And it's just going to check if a number is equal to 9 factorial. Return number equals this. That's basically it. So we don't need this whole thing. That was just to actually find the value of 9 factorial. We will be using this though. Okay, cool. So let's go back to this. Now we've got these arrays here, and we want to give them some length. So we'll keep it 9 for now, and we'll fill them with 1s to begin with, because we basically want to multiply them by every number that we encounter, right? So we find some numbers here, we want to multiply them in. So, okay, specifically what do we want to do? Well, we're not going to have this anymore, you know? We're not going to say like rows at I at number minus 1. It's just going to be like rows at I, because that's pretty much it. Rows at I is, like rows is just one array now. So rows at I is just going to be one of those numbers within the array. What do we want to say about it? Well, we want to say, let's multiply that by the number. That's basically the idea. We want to do the same thing with the columns. Multiply it by the number. And then we want to do the same thing with the squares, the kth element of it. We want to multiply it, not add it. Let me change that in just a sec. We want to multiply it by the number. Yeah, there we go. And okay, so first of all, let's just return rows. We'll see what we're getting from that. And whoa, okay, so we're getting 9 factorial, 9 factorial, 9 factorial in most of these places, but not in the first row and not in the second. Well, this is the example we were looking at that had 2 2s in the first row, and there was some issue with the second one as well. Oh, it's got 2 8s. Yeah, okay, so basically these are not going to be 9 factorial because they didn't have the numbers 1 to 9. Okay, so basically we could say something like this. Rows dot every. Okay, is everything in this row 9 factorial? And that's what our function is here for, right? Rows dot every 9 factorial. So this should give us, yeah, some of the right answers, but not all of them. This one we're saying it's true, but it really should be false. I'm assuming that's because it's either one of the columns or one of the squares that that is lacking. That doesn't have every one of its elements being a 9 factorial. Now basically the way this everything is working is if there's one thing inside the array here that, if there's one thing inside the array that doesn't have that property, it's going to return false. So it's kind of like, it's basically like doing a reduce with an and. So there we go, let's submit that, and okay, it's passing the visible test. Does it pass the hidden? Yeah, it does. Okay, so I think memory-wise that's a bit better, because instead of 3 matrices, now we have 3 arrays. At the same time, I think it's not any different in terms of complexity, because it's not like the inputs here are going to change size, you know? Like, we're not going to have a bigger array of rows, calls, or squares. Like these, it's a fixed size. So in terms of complexity, it's not really going to matter very much. Okay, now just to return to this thing over here, I just want to clarify this rows.everything. It's, I keep saying it that way. This thing that's rows.every, it's basically the same as doing something like this. Rows.reduce. So we're doing a reduce here, A, B, and we basically want to say, or wait a sec. Sorry, we've got to do a map first. Rows.map, and on this, we basically want to say 9 factorial, right? Rows.map 9 factorial. So it's basically going to say for every number inside the array, return or convert it essentially to whether or not that number is this one. Okay, so that's the idea. Rows.map 9 factorial. It's just converting these all to booleans representing whether or not the number is 9 factorial. And then on there, we want to do our reduce. Let's just say A and B are our inputs, and we want to reduce that to A and B. So that's the same thing. This is the same as doing the every on this one. Okay, so it's basically saying for each of your elements, check if each of them is equal to 9 factorial, and then basically reduce it. Just say if the first one is 9 factorial, and the second one, and the third one, and the fourth one, for all of them, right? So that's every. That's a nice built-in. It's really useful. There's also a similar one called sum, S-O-M-E, which I feel like we've used, but anyway, the point is, this is good stuff. These are nice tools. This is working for us. So this is pretty good. But I have to say, I think it could be a bit better. And we've talked about time complexity. We've talked about space complexity. The idea that like these are pretty much the same in terms of complexity, it doesn't mean that one isn't more efficient than the other. So even though they're equal time complexity or space complexity, or at least I think so, that doesn't mean necessarily that they're going to have the same computation time. I still think that this one is going to take up less memory and execute faster. Well, potentially. I mean, this one sort of had like a return within here, so it's going to return as soon as it knows that it's not going to work. So maybe the computation time is actually faster than the other one. Then again, it's got to create all these matrices. I don't know. We'd have to test it out. But the point is, for this anyway, I think it could become a little more efficient. Again, I'm not really going to change the time or space complexity, but I am going to change the efficiency of it. I got a hot tip recently. There's this thing called a typed array. So we've sort of touched on this before, that in JavaScript, arrays are a bit different. Hey, stop it. Arrays are a bit different from other languages in the sense that they don't all have to have the same type. Like you could have a string and then an integer and then a function. You know, it's like whatever type you want. And also we can extend them. We can change the size of them very easily. So they're a little more dynamic in terms of their memory. The thing is, that's like a lot of extra structure that we need to worry about, right? Because we don't know who's going to be in that array. It's like, okay, let's say you're trying to plan like a dinner party, right? But you don't know what everyone's dietary restrictions are, and you don't know how many people there are going to be. So, you know, maybe you've got to have like some gluten-free stuff on the menu and some vegan stuff and paleo, like all these kinds of things, right? Maybe there's like maybe someone's like a raw food or like a fruitarian or something like that. The point is, if we don't know what to expect, if we don't know who's coming to this dinner party, and if we don't know how many people there are going to be, we really need to prepare. You know, we're going to have a lot of stuff on hand, sort of thing. Whereas if you know, for example, okay, it's going to be 8 people and all of them are vegan. Well, it's a lot easier to plan for, you know? I mean, you know exactly what to expect. So you don't need to get as many groceries. You don't need to be prepared for as many unforeseen possibilities. So a typed array is the same sort of thing. It doesn't need to keep as much additional structure because it knows what to expect. It can make more assumptions about the data that's going to be in here. So basically, typed arrays, there are lots of different types of them, but basically they could just be integers, and specifically we can make them like really small, like 8-bit integers. The U stands for unsigned, as in like not negative or positive. We can have 16-bit integers, 32-bit integers. We've got floats of various sizes as well, and this sort of tells us how much like the size it's going to take, how much memory it's going to take up. So that's pretty cool. Now, in terms of what we're doing, we need for our numbers in here to be as big as, what was it? Yeah, this, 362,880. So in terms of which one we're going to use, we're going to have to bust out the full power of the int32 array. And I'll just use an unsigned one because why not? We're not going to have any negative numbers in here. So I think it's going to save us some time. You know, what I've heard about these typed arrays is apparently in terms of computation time, they can be up to like 10 times the speed of a traditional JavaScript array. So that's pretty good. All right, so we're going to use this one. We'll do a uint32 array. So we basically need to instantiate it sort of like this, new int32 array, and we can give it the length that we want. So that's kind of nice. So let's do that. So instead of these, instead of array at 9.fill1, let's say new uint32 array at 9.fill1. So the rest of it is the same. There we go. Paste that in and paste that in. And in terms of how we interact with it, it's pretty much going to be the same as other arrays we've dealt with in the past. So let's try running the test. And we see we didn't have to make any other modifications here. You know, like all of this syntax still works. All of this syntax still works. So the built-ins that we have for arrays are almost all going to work for these typed arrays as well. There are a few that won't work, like I think .push and like shift and that kind of stuff, because we're not going to be changing the size of these things. They're going to be a fixed size, again, so that like we know a little more what to expect. And we're sort of filling in the interpreter. We're saying like, hey, don't worry about it. You don't need to worry about this array changing size or having anything other than these big integers. So this is a little nicer, I think. I mean, we basically made one small change and we get a lot of free efficiency from that. So that's pretty good. So, okay, that's another way of doing it. We'll keep that way in mind. Let's copy that, because I want to change this slightly. I'm thinking, you know, like that was good, but because we're multiplying these numbers, like they could be pretty big. So instead, I'm going to say, well, what if instead of 9 factorial, let's just say 9 sum. So in other words, the sum of all the numbers from 1 to 9, which, well, we've got that trick, care of Carl Gauss, right, where we can say n times n plus 1 divided by 2, and that's going to give us the sum of all the numbers up to that size. So basically 9 times 10 is 90 divided by 2, 45. So we should be getting 45 in each of these things if we're summing these up. Okay, now here's the thing. One issue with this, actually, sorry, not an issue. This is actually a good thing. I'm going to get rid of the fills here because I want to start at 0 now. You might be thinking, well, shouldn't you do fill 0 then? Well, no, because that's actually a very cool thing about these typed arrays. Unlike a traditional array, these actually, by default, start with all zeros in here. So that's actually really good, because normally they'd be like all nulls and stuff like that. I want zeros, so that's one less step I have to worry about here. So that's just an added convenience. Now again, here we don't want to be adding, we want to be summing. Sorry, we don't want to be multiplying, we want to be adding. That's what I mean. Okay, and 9 sum instead of 9 factorial. So is this going to work? Let's find out. Very suspenseful moment here. It's not working. Well, it mostly is, actually. It's working for almost all of these. But look at this. I think they saw this coming. I think whoever made these tests was kind of expecting someone would pull this sneaky trick over here. So yeah, they put in this, which is basically failing as hard as you possibly can in every possible way. I mean, if we look at like our first algorithm here, and this is the nice thing, like by the time we're on to the second element, this is going to be like, whoa, no, there's already a 5. We're done. So in that sense, you know, this one was pretty efficient for something like that. It fails as fast as possible, so that's good. If it's going to fail, it'll fail right away. But yeah, for this, we need a way of dealing with this. So basically, we'll just add on a little bit of extra structure here. We'll say let nums be this other new uint32 array of length 9. And basically, the idea behind nums is that it's going to be sort of counting, just sort of making sure that that we've encountered each number 9 times. That's basically the idea. So nums at number, and we got to do the -1 again here, and we're just going to do a plus plus. So we're doing the -1 because again this goes from 0 to 8, number goes from 1 to 9, so the index would actually be 1 less than the number. We're incrementing it, so we start at 0 and we're doing it plus plus. How many of each number should we find? Well, 9 of each number. There's 1 in each square, there's 1 in each row, there's 1 in each column. So basically we should have exactly 9 of each. So we're going to include that here. We're going to say and nums.every, and we'll say x is mapped to x9. Okay, there we go. And we'll put that on the next line just for consistency. Oops. backticks. Sorry about that. Let's run that. Let's see if that works. Ooh, it works good. Okay, so can we submit that one? Is it, yeah, it's working. Okay, but here's the other thing. Check it out. This, 45, that's not a big number. That's much smaller than what we were dealing with before. So let's go back to this. In fact, let's go back to our typed arrays. Look, we could get away with using just a uint8 array, you know, or even just an int8 array. Like it's going to be fine to use those because 45 is basically the biggest number we're going to have to deal with. So let's change these 32s to some 8s because, you know, that's going to save us, I guess, a pretty significant amount of memory. That's kind of not bad. So there we go. Is that going to work still? Ooh, yeah. See how fast that went? Oh, satisfying. Okay, cool. So I like that even better. Pretty nice. Okay, cool. And that's still working. It's still passing all the hidden tests and all that stuff. Well, that's great. Feels good, right? Okay. So let's see. What do we want to do next? Well, I want to try a slightly different approach to this problem. So we'll copy that one. We'll archive it. We'll say that's, what are we up to? 3. Sudoku 3. All right. Get a bit of extra space in there, and we'll paste that in. Okay, so what do we want to do differently with this one? Well, I want to think about this in a different way. Okay, so basically, okay, I want to think about this not in terms of rows, not in terms of columns and squares and all that stuff. Well, I mean, yeah, ultimately in terms of those things, but we're going to do it a bit differently. So we've got all this stuff here, and you know, we'll think about what we want to return later. This is basically the structure that we want to maintain for now. Okay. In fact, no, we don't even need this one. Okay. This is basically the structure we want to maintain for now. And the idea behind this now is I want to look at it in a different way, and specifically what I want to say is we've got a bunch of different outcomes essentially. So like a 3 appearing in row 1, that's one of the outcomes. A 5 appearing in column 6, or I guess the column with index 5, that's an outcome. So basically that outcome should only happen once. You know, if you find a 5 in column 5, that should only happen one time. You know, whether it's over here, whether it's down here, it doesn't really matter. If the 5 is in that column, that should only happen once. So if it's already happened before, that's no good. Basically, the reason I'm mentioning these things in terms of like outcomes is I essentially want to map each outcome to a hash value. So I'm going to say, like, you know, a 3 appearing in row 1, it doesn't matter where it appears in row 1, the fact that it's in row 1 should be represented by a number. That's basically a hash value. And then we'll represent every outcome by a number. So how many outcomes do we have? Well, basically, we've got 9 possible numbers. Let's say for each row, right? We've got 9 possible numbers. So each row has 9 outcomes, right? There's a 1 in row 1, there's a 2 in row 1, there's a 3 in row 1, etc. And we have 9 rows. So basically for the rows, we have 81 different outcomes. 9 different numbers in 9 different rows. So 9 times 9, we get 81. Now, same thing for the columns. We're going to have 81 possible outcomes for the columns, and same thing for the squares. So in total, we're going to have 243 different possible outcomes. That's the idea. So how are we going to get these outcomes? How are we going to actually get like a hash value for these things? Well, basically, let's do it like this. So we'll say let row hash, I guess I'll call it. Yeah, let row hash be assigned the value of. And basically, it's going to be our row, which is 1, right? So, I. It'll start as 0. But so I is basically going to be our, like, what row we're on, right? It's 0, it's 1, it's 2, it's 3, etc. And then we're going to take that, we're going to multiply that by 10, and we're going to add to that number. This is just to turn this into a 2-digit number. So we know number goes from 1 to 9. So basically, for this, we will have like 0 times 10 plus 1 to 9. So this, for the first row, will cover 1 to 9. For the second row, we'll have 1 times 10 plus 1 to 9. So it'll go from 11 to 19. For the next row, 21 to 29, 31 to 39, etc. So basically, 89 is the last value that this is going to cover. Okay, and then we'll do the same thing with the column. So column hash is going to be j times 10 plus number. Same sort of thing. But the problem here is that these are going to interfere with each other. We want a unique number for every outcome. So right now the problem is that if we had, let's say, like a 4 in column 3 versus if we had, let's say, a 4 in column 3 versus a 4 in row 3. Right now, these would map to the same hash value. We don't want that. So to make them mutually exclusive, I'm just going to add on 100. Okay? Because we know that this is not going to cover 100. In fact, I could get away with just adding 90, but who cares? The point is, we want these to be mutually exclusive. And the reason for that is, well, they've got to be unique, right? Okay, now here it's going to be k times 10 plus number. We're just going to add 200, again, to make it different from all these. So this is basically going to cover numbers that are within the range 0 to 100. It's not going to hit all of those numbers, but they're all going to be within that range. This one is going to be between 100 and 200. This one's going to be between 200 and above, I guess, you know. Okay, so basically we've got all these hash values now. So what are we going to do with that, though? Well, we could do something like this. You know, we could say something like, let archive be assigned the value of just this object, right? And it just starts as just being like an empty object. And then for each of these, we could say like archive at row hash assign the value of 1. Archive at column hash is assigned the value of 1. Archive at square hash is assigned the value of 1. Okay, so we're doing all that stuff. But the thing is, if it had already been 1, you know, so if any of these things, and I guess I'll just do a sloppy copy here, and we'll do or. So this is kind of like in our first solution, the way we were saying, well, if any of these things already exist, if we've already encountered any of these outcomes, then we basically want to say, no, that's going to be false. If you've already encountered the outcome and you're finding it again, well, this must not be a valid Sudoku. So we're going to return false in that case. And then if we make it to the end without actually triggering the false there, then we'll return true. You've earned it at that point. So let's run that. Oh, nice. Okay, so that's pretty cool. I mean, we're basically just using numbers here. We just have one object here now. And it's going to contain, at the very most, 243 elements. Okay, so that's pretty cool. It's pretty not bad. But I want to talk about something else for a second here, because something was recently brought to my attention. This is a lot like a hash table. I mean, it's kind of sloppy in some ways, but it's sort of like a basic hash table idea. And I had mentioned in a previous video, I think it was 55, I was kind of like, oh, I don't think JavaScript has a built-in for hash tables. And one of my YouTube viewers, so a special shout out to username Monolism, for pointing out that there actually is a JavaScript built-in called map. And map is basically doing the job of a hash table. It's sort of like our hash table built in for JavaScript now. So cool, that's a good thing to have. So in terms of how we're gonna work with this, so we've got, .has instead of like a .includes or something like that. We've got a .get, we've got a .set. So kind of object-like in terms of like having our getters and setters, our mutators, and I forget the other one. But anyway, the point is, this is what we're going to use now. It's going to be a map, because that's basically what we want, right? So instead of making it just a generic object, we'll say it's going to be a new map with just sort of an empty constructor here, We're not going to put anything in there. So basically, okay, what are we going to do from here? Well, instead of these, instead of like, archive at row hash, we'll say archive dot set, and the value of row hash is going to be 1. Yeah, that's the idea. And maybe I'll just copy this one over here. Good. And then we'll say this one is going to be the column, and the next one is going to be the square. Okay, cool. Now I do need to make a couple other changes here because this I don't think is going to work so much. So instead we're going to do a dot has for all of these. Dot has and dot has. Okay, so using the syntax we just found, and there we go. Okay, are there any other changes that need to be made here? Let's find out. Let's try running that, see what happens. Ooh, pretty cool. Okay, so that's pretty good. I like that. Yeah, nice stuff, nice stuff. Okay, so this is good. I like the idea of using the map here. I think that's smart. It definitely fits the situation here. Let's just space those out a little bit. Is it going to pass the hidden tests? Let's just, I can't remember if I ran the test or not. Okay, great. Looks good. So we're going to copy this thing, and are we just going to do one more of these things? I think so. Yeah, we'll do one more of these. And then we'll, I think, call it a day for now. So, okay. One of the things I'm noticing here is I thought, we're using these hash values. This is a perfect opportunity to use a hash table. But then I realized, we're not really using the full power of the hash table here for 2 reasons. Number one, our indices are just numbers. It's not really that special. Part of the advantage of using a map is that your keys can be anything. They don't even need to just be strings. They can be functions and stuff like that. And the idea is that it's going to hash them as a value to deal with that behind the scenes. So here, I don't know if this is really the best use of map because these are just numbers, and this is just a 1 or a 0. It's basically a true or false. It's are you in the map or not? Are you in the object or are you not in the object? So basically, anytime we're talking about whether something is in the object or array or whatever or not, and that's it, we don't need to know, because, all I'm trying to say is these are never going to be anything other than 0 or 1. It's basically, are you in there? Are you not in there? Okay, so because of that, we're going to use something different. So instead of a map, we're going to use a set. So that's what a set is basically all about, right? Are you in the set or are you not in the set? That's the idea. So we're going to have to change the syntax a little bit, not that much actually, because has actually does work for a set. So that's not bad. We will need to change this part down here. So basically, we could do I think something like this: archive.add row hash, archive.add column hash, and archive.add square hash. Let's try that. Is that going to work? Oh yeah, it does. Works nice. But here's the thing. I'm thinking maybe there's a more efficient way we could do it. Actually, okay. I'm going to write this in such a way that's maybe going to look more efficient. I don't know if it's truly more efficient. I was thinking there's multiple elements here. We're adding multiple things at a time. So maybe there's a quicker way of doing that. So basically the way I came up with, and I don't know if this is good because I am technically instantiating a new object here, a new set object, but basically I said something like this. It's a set, it's going to come from an array. It's going to be an array that contains row hash, column hash, and square hash. But also it's going to contain all the stuff that it had before. Okay, so instead of this now, instead of these, I'm just going to try this one line. We'll see if that works. Ooh, and it does. So that's pretty cool. Okay, not bad. The next thing I'm looking at is this. We've got 3 things here too, and I'm thinking, well, is there a way of checking easily if it has any of those things? And again, I mean, maybe there's a better way to do this, but I thought of one way, which is basically this. We could say, let's say we've got this array containing these 3 elements, and we basically want to say, well, out of these 3, is there at least one of them? Is there some of them that's going to have that property that basically the archive has that element? And if that's true, well, that's really all we need to hear. I mean, that's enough to say return false, right? So is that going to work? Yeah, it's going to work. Okay, cool. So this is pretty nice. I mean, we basically see the whole code here, and it's looking pretty good, I'd say. Let's submit that one last time. And okay, I think I'm feeling pretty good about this overall. There's one thing I'm going to change though, because I mentioned it earlier, and I think it's probably worth showing at least. I want to do this with one loop. So instead of like these nested loops, I want one that's basically just going to go, instead of like from 0 to 9, 0 to 9, 0 to 9, 0 to 9, just go from 0 to 81. And then basically we'll say we want the rows, we want I to just be, I guess, like the floor of n divided by 9. So we'll say let I be assigned the value of Math.floor and divided by 9. And we'll say let j be assigned the value of I mod 9. Okay, so like if we divide by 9, what's the remainder? So, I mean, just going from 0 to 9, this is, or 0 to 8 anyway, this is just going to be pretty normal. J is just going to be n. And then for the next one, basically the idea is that we're going to start at 9. Well, mod 9, that's 0. 10 mod 9, that's 1. 11 mod 9, that's 2. So basically that's the idea. We're going to have I and j that are just based on that. And I guess I should put k before number. That might be nice. Baby Sean asks, isn't hash table most in big O of 1? You mean like lookups and stuff like that for the hash table? Yeah, I mean, from what I understand, it depends on the implementation. So like if you're using a linear probing technique in your hash table, then it at best would be big O of 1. At worst, it would be big O of n. So that sort of stuff, like linear probing, getting right into like the nitty grits of hash tables, I would check out, I think it was video 57, task 57, file naming, I think it was called. So if you want to know everything I know anyway about hash tables, it's in that video. Okay, so is this working now as a single loop? Yeah, it's working. Okay, cool. That's great. We'll submit that. And actually, you know what? There's one last thing I want to do. I'm using a lot of lets here, but I'm thinking I can get away with using constants for a lot of these because it's not like we're really reassigning a lot of these values, right? Like, I don't think we're really changing any of these. Are we changing any of these? Can these all be constants? Yeah, they can all be constants. Now, this archive, yeah, obviously we're changing that. So we couldn't make that one a constant, right? Because like it's not immutable. We're making changes to it the whole time, all the way through. So wait a minute. So why is that? That seems like it should have thrown an error. Like, whoa, hold on a sec. You know, type error or something like that. This is a constant. You can't be reassigning that. And this addresses a really important misconception about const. Okay, so I saw this article recently. It's this one. So this is by this guy, Matthias. So basically, really smart article here. I mean, basically it points out that the misconception that constant is immutable, like that it's saying the variable is immutable. It's not the variable itself that's immutable. It's the binding that's immutable. So what we're trying to say is that archive will always be pointing to this set. It's always bound to this set. Archive, we're not going to say, okay, now archive is a new thing. Well, technically we are kind of doing that. So that's kind of strange, actually. I'm a little surprised that this one actually worked, just mainly because of this line here. But anyway, that's one thing I didn't want to mention because I think I've kind of fallen into this trap before, saying that a constant is something immutable. It's an immutable binding. So I'll try to be careful about that. Can we submit this? Is it going to work? Is it going to be fine? It's going to be fine. Okay, great. So I think that's it for this one. Let's wrap it up. Let's get the heck out of here. Nice job, everyone.